to their powerful applications in modern artificial intelligence and generative AI. Without further delay, it is my privilege to introduce our speaker to today's session. Today's session is special to us because today, for the first time, one of our own senior lecturers, Dr. Janaka Wijayakulasooriya, from the Department of Electrical and Electronic Engineering at the University of Peradeniya, will be delivering the MathXplore Talk. Our speaker today, Dr. Wijayakulasooriya, graduated with first-class honors in Electrical and Electronic Engineering from the University of Peradeniya in 1994 and was awarded the Professor Peradeniya Gold Medal as an outstanding graduate of the faculty. He later obtained his PhD from the University of Peradeniya and Newcastle, United Kingdom. Over the years, he has served the university in several leadership roles, including head of the Department of Electrical and Electronic Engineering, the director of the Computing Center. He has also made significant contributions to engineering education through IEEE Sri Lanka and has inspired countless students and teachers through workshops promoting innovation and creativity. We are truly fortunate to have one of our own faculty members sharing his knowledge and experience with us today. Ladies and gentlemen, please join me in giving a warm round of applause as I invite Dr. Janaka Wijayakulasooriya to conduct today's session. Sir, the stage.
Okay, good morning everyone. So, first of all, I would like to thank the Mathematics Society for inviting me. Before moving to any lecture of this sort, I usually do one ritual, and also it will be giving you some point to think also, especially make your learning subject easy. So I spend around 5 minutes on this slide. That is to dedicate this lecture, right, to every teacher who inspired me to use mathematics not to solve problems, but to see the world differently. The reason why I want to say this is, I think that is the part which is important for you. I remember from grade 6 to 8, I became bit by bit weaker in mathematics, and when I came to grade 8, I was getting for term test marks like 20, 21, 23, in that range. So the school at one time in grade 8, before going to the O-level class, they decided to call the parents of weak mathematics students and ask them to, actually what they asked was to not to sit for the O-level exam. So during that vacation, my parents have sent me to a teacher in a rural school. What he has done was not anything. He hasn't taught me mathematics, but he did exactly that thing. He changed the way I look at the world through mathematics. After that, because of his intervention, he passed away 2 years back. I started again developing the interest in mathematics, and to cut short the long story, at the end of my university life, I ended up by winning the E.F. Bartholomew's Prize for Engineering Mathematics. So the message for you is, if you try to look at, usually consider this as a difficult subject, but if you try to use this to see the world in a different angle, I think mathematics becomes one of the most interesting subjects. So with that invitation, I would like to move on to the main overview of the presentation. Today, my topic is from linear algebra to GenAI. But in between the linear algebra and GenAI, there is another layer that also I will touch upon, that is non-linear algebra. Of course, there is, I don't know, we can ask from Dr. Ishaq and Professor Sushant whether there is a subject, but I have seen some books inviting people to develop subject of that nature. So anyway, since I am mainly focusing on my interest area, that is computer graphics and videos and so on, I would like to start with the basic concepts of human vision very quickly. Then image representation mathematically, because those fundamentals you should know to understand something. Then color spaces, and then I have named it as eigen spaces, because eigen analysis is something very close to you because you have learned it already. So how to represent some of these information using eigen analysis, and then from there the latent space, which is the general term used for all the nonlinear spaces, and finally part of GenAI, not the complete set. So I'm not going to explain this right. You need to, I assume that you all have some fair idea about vector spaces, what the vector actually means, and also eigen analysis. What is the, always while learning this, I think always try to learn what is the physical meaning of each of these things. That will take you more deep, I think. And then principal component analysis, I hope that also covered in our undergraduate courses. And finally, something that I was very interested when I was a final year student, Kahunen law transform, which is extension of principal component analysis sort of. Now, in Fourier transform, we map whatever the information we have onto sinusoidal and cosinusoidal axes. Similarly, here we are mapping the information onto principal axis. So those are the basic background. So first, quickly going through the human vision, I have around 2 slides on that. Basically, we perceive information, different species perceive information differently. Humans, they have these 3 types of cons and rods. And due to the responses that we are getting from that is the biology and physics side, we perceive color. It will generate electrical signal which takes it to the brain, and that's it. I think that explanation is enough. Then quickly going to the image representation. Like in any information, images also can be represented as vectors in mathematics. Basically, black and white images, then grayscale images, and color images. We can represent it as a matrix, and finally, for the analysis purpose, we flatten it and convert it to one-dimensional vector. Right? So any image, for the analysis purpose, we treat it as a one-dimensional vector. Then we can apply all these other mathematical analysis techniques. Then we come to the color spaces quickly. In color spaces, the most commonly used color space is the RGB. RGB is actually a vector space. Right? Although it comes from the biological roots, we can plot any pixel value. Please keep this in mind because I am going to use this as a case study later. So in the RGB space, we can put any pixel as a vector, R value, G value, and P value in a 3D vector space. Then we have other vector spaces. One of the most commonly used vector space in computer graphics and various other applications is HSV. There's a direct mathematical link between RGB and HSV. Just to tell you why we are going for different spaces is HSV means hue, saturation, and value. If you take this top circle, it is called as color hue. Right? If any of you are working with video editing, I think you may be familiar with this because we are playing a lot with this when you are making videos more attractive. And also there are certain theories which can be mathematically explained. That is the beauty of that. So for example, now in HSV, if you take this H space, that is the hue space, if you take 2 opposite colors, they create some psychological effect on people. For example, one of the most popular color schemes used in video editing nowadays is called as teal and orange color grading, or teal and orange color palette, something like that. And they are exactly at 180 degrees apart in the edge space. Right? So anybody interested in relating these things with mathematics, I think they can find a lot of areas to explore. Similarly, things like color trade. I have taken only 2 examples because there are a lot of other mathematical models here. The triangles, or we call it as triad, is also used to create some psychological impacts. We don't know why it happens, but psychologically it has been proven. For example, if I take the Superman logo, right? The logo, I don't have a picture here. He is wearing a blue shirt with the red color S letter with some yellow background. So these 3 colors are exactly coming in this color trail. Right? So like that, anybody like to go in that direction from mathematics, I think you can explore a lot of things, especially as far as I know, there are no much work in establishing a scientific relationship or biological or psychological relationship between these things and number theories. So I'm just talking about some possible research here. This is the direct RGB to HSV conversion. You can see it is a bit nonlinear mathematical conversion. Bit nonlinear means not exactly linear, it is piecewise. Then when it comes to engineering, there are a lot of applications when you analyze on RGB and HSV spaces, especially if you want to analyze metallic surfaces, gear wheels, engine tracks, things like that in mechanical engineering, civil engineering, concrete tracks. We are going for these color spaces and analyzing. Apparel industry, defects in clothes, we have done some projects in that area where you get the RGB image, convert it to HSV image, and then combine the two and get information to identify defects. So if you are interested, you can go through those research. I am not going to explain. And another very beautiful area is multispectral imaging, where instead, in addition to RGB, you will try to visualize any image using multiple spectrums. And using that, you have again a lot of mathematical modeling and wide range of areas. So that also very good area if somebody want to work, and also hyperspectral imaging. So I quickly try to go through other possibilities before coming to my main area that I am going to present today. First, eigenspaces, because that is very close to you and simple to understand. I will use that, and then we will see what is a latent space means and how it is used in GenAI, because in GenAI there are different models that we are using. One part comes from this latent space. So before going further, I would like to, because I told that any subject becomes easier if you enjoy it. Right? So this is how my enjoyment comes, because to go through all these difficult stuff, I should have some enjoyment or inspiration. So first let us enjoy one song that I have done recently. But then I will take 2 examples from that song and explain how it is mathematically modeled and done. So please carefully watch, because I am going to use 2 examples from here. and all the video parts are done using GenAI. So although it was a little bit long, I decided to play it full because, as I mentioned, what is important is the inspiration. Right. So we will move on to GenAI. First, I will have an overview, but I am going to take 4 examples from that video and explain you the mathematical basis behind that. First, color grading. You may have seen, if you have seen some difference in the color schemes used in that image, how we can use it, because it is very simple, so everybody can understand, and I am pretty sure that you also can write a code today evening. Right? That is that simple. And then the facial animation, how the emotions are modeled, and then more body modeling, and finally body movement animation. So those are the 4 areas that I am going to concentrate. GenAI is a very broad area, so we don't have even time to cover everything today. But 2 main points are, one is this latent space, the other one is the diffusion model, but I am not going to touch on the diffusion model, but that also heavily relying on mathematics and very interesting model to study, where you are generating information from randomness. So very high level random modeling or statistical modeling is involved here. But I will mainly focus on this one, which will be mainly involved in generating phases and how to continue the same phases, changing emotions and things of that nature. So latent space is basically, think of something like this. Later I will explain the same thing using principal component analysis. But think of something like that. You have a very high dimensional non-linear space where you can map any image, which will have different clusters forming like this, which are corresponding to different things. For example, your emotions. Right? There can be vectors representing your emotions. There can be vectors representing your head pose. There can be vectors representing your skin color, ethnicity, things like that. So in the latent space, which is a hugely nonlinear space, you can extract this information. Right? So later I will explain what is the latent space is. But this is one example, just mapping your face and various other things into a vector space. Although it is drawn 3D here, it is a multidimensional space. As I mentioned, then you can find various axes. Along them, emotions are changing, skin color is changing. So it is just a matter of then finding some interpolation paths along those axes to change emotion, poses, and so on. Right? I will demonstrate one using a program. So the interesting idea is, when you map all these things into a vector space, there are enormous number of things that you can do. You can create new information. Right? This is one commonly used example for explaining this. For example, let's say you have a vector in that space explaining a key. Right? And also you have a vector explaining a male, and you have another vector explaining a female. Right? Just assume. Later we will see how they are derived. So one simple equation given is, if you want to generate a queen, right, it is like you are subtracting the male vector from, so it is negative male vector added, and then the positive female vector is added. The resultant vector gives you a queen. Right? And with this, you will have some statistical distributions of the vector L that we will see later. Okay, now rather than try to understand it this way, we will try to understand it through certain case studies. I am pretty sure this will be a very simple one to understand. So this is a very good beginning point. Let's say something like this. Usually, let's say somehow I generated this picture, right? And after that, I like to give a certain color grading to that image. Usually in video editing, what we do is we change the color axis until we get the correct one. But in GenAI, usually what we do is we give something like a sample image which we really like. For example, I can say create a sunset color grading to this image. Right? Or I can give a sample image like this. Usually in some of the video editors you have this feature. You can give a sample image and say, okay, get the color grading from this image to this image. So we will use a linear space using principal component analysis, because that is something you already know, to see how this can be done. So basically, if you take the first image, you can represent it in RGB space like this using vector. So all these dots are representing each pixel of the image in the RGB space. Even here you can see it is not randomly distributed. Right? When you plot any picture onto the RGB space, you can see there are certain vector directions here. The whole data set is directed towards particular direction. For example, here it is going through the blue direction. That shows something about the color grading of that original image. So if I do the same analysis for the sunset image, I get this is coming this way, which is to the red axis. So it has more reddish and yellowish color grading. So now I have two vector spaces. One simple thing you can do is, we will start with what we already know. We can get since we know that there are various directions, next thing we can do is we can go to principal component analysis and try to obtain the principal components of these two. Right? So this is from a program that I have written for those two images. And it seems there is a problem of playing videos here. Anyway, you can see it from here. So I can explain this without video, but there are some other videos I have to. Anyway, here the red dots are representing the sunset image, and blue dots are representing the original Giridevi image. And you can see after you get the principal component, there are three principal components in the first one and second one, the red axis and blue axis. Now if I want to transfer the color grading of the sunset to the other one, while containing the original image, what I do is, I do an axis transformation, that's it. Right? This is how I do it mathematically. First, let's say the VA is the eigenvectors of the sunset image, and mu A is the mean value of the sunset image. Right? And similarly, for the Giridevi image, mu B and mu B. So first what I do is, I will move that cluster of the original image into the center. We can simply do that by subtracting the mean value. That's what we are doing in principal component analysis also. Then I map it onto the eigenvectors of that space. So the YB that calculated here is simply the original matrix subtracted mean and multiplied with the eigenvectors. Then I map it onto the sunset image axis, and then at the mu value of that. That's why I told even you can write an algorithm today because this is so simple. And when you do that, you will find the same image will be there, but the color grading of that image comes here. This is the practical results you get. And again, unfortunately, I think the videos are so here the green color dots are the newly transformed image. So this is used for many things like color transfer, style transfer. For example, I can transfer different ethnical styles like this. So let's say you have a art by Picasso. So you analyze all the principal components of Picasso art, and then you want to transfer one of your drawing into Picasso's scale. You can try these things. Very interesting area and sometimes dangerously addictive. Right? Because it's so much, because I have tried that for Van Gogh images and it is very interesting. Then the next one I am going to show is the for some of these things you need animation. So let's take this part, how the face is animated, like with different emotions. So just to explain this, because this also works well on the linear space as well. You don't need to go to a non-linear space. Only if you want to change the pose of the head, you need the non-linear space. So I will explain this using principal component analysis again. So I have taken 16 different emotions from a photo of one of you. So anger, neutral, happy and sad. Then what I do is map all these 16 different images onto feature vectors. This is how it is done. So each image comes to a column, and the column is around I think more than 1 million dimension, because these images are 1024 by 1024 images. I'm using just grayscale images. So 1024 multiplied by 1024, which gives you more than 1 million into 16 matrix. Right? So you have this matrix. The next challenge is to find the principal component of covariance of this matrix. So mathematically, this is also a very beautiful point in mathematics. In mathematics, in order to find the covariance matrix, what is the technique? This is the basic definition. You get x multiplied with x transpose, and then you are going to find the eigenvectors of that C. Of course, there is mean reduction and so on, but I have seen to put that there. So, but this is what the mathematics says. Right? Find the covariance matrix of this, and then do it. But then comes the real scenario. That is, this is the continuous struggle between mathematicians and engineers. Right? Mathematics say, okay, this is the way to do it. But the engineer who is going to write this algorithm says, no way, because the dimension of that matrix is too high. Your computer gets stuck, or it will go out of control. Right? But then he says, okay, in real world, I don't want to calculate all the eigenvectors. Few of most dominant eigenvectors are enough. Right? Then it's a sort of deal between mathematics and engineering. And then some people have found a very interesting technique. So this is where actually real interesting research happens. This is not a big thing. Mathematically, you can prove that uh, rather than trying to find the eigenvectors of that big matrix, if you find the small matrix, which is only 16 by 16, because we had 16 images, if it is 100 images, we will have a 100 by 100 one. Find the eigenvectors there, multiply it by x, and you are going to get the eigenvectors if you normalize them. Right? This is a theory developed by Turk and Pentland in 1991. Right? So I think this is one thing I have seen really beautiful. There are a lot of examples like this, which shows sometimes we find something difficult, but challenged by engineering, and then the mathematicians always come with different techniques. So that dialogue should be there. So that is why I have put this slide. The true elegance of mathematics is unlocked by the chaos of engineering. Think about it. Right. So we can, that way, using that method, we can calculate the eigenvectors. And I have here plotted the first 9 eigenvectors of the phase, emotion phase data set. So you can see it's not that clear because you are getting it in the low dimensional space. So those are the first 9 eigenvectors. Now, if I want to synthesize the phase, I can combine few of these eigenvectors weighted by some weighting factor, and I can get. Right? So this is the synthesis part. So these are the eigenvectors, and this is the phase synthesis equation. But you can, I will show you here, even by using 2 eigenvectors, I can get a high resolution good image. So, and also interestingly, different emotions are mapped onto different parts. Still we are working on the linear spaces. So happy is on the left side, happy for phases. Then sad is very close to neutral, and angry is up there. So then I did the program to move in this space. So if this asterisk shows me where it is presently, and if I move that, now you can see the emotions of this space changes according to the position of that red asterisk. So I will slide this part in different emotions. I have shifted it a little bit up. So the second vector weight factor is up. Now you can see. So like that, you can change the emotions, and then by programming parts, so if you get linear and nonlinear interpolation between various spaces there, we can create animation changes, like from happy to angry. This is using more principal component. In the earlier one, I have used only 2. But let's say we are moving on a multi-dimensional space, so you get more natural images. And then finally, you can get, in a nonlinear space, you can get all these things. So this cannot be done in linear space. So this was generated using GenAI, where you can see even the head pose is changing. And finally, you can use it in creating videos. Okay, so that is the demonstration. But then I have tried the same thing on different faces, different people. Earlier it was only one person, so that is why it came perfectly. But when you do it for different people, same emotion, neutral emotion, and these are the eigenfaces I got. And but you can see it is here also I used three principal components to generate, but it is not that clear, especially ladies, right? Because their feature space is coming in one corner. But when you move to that only there was one male, when you move towards that, you can get it clear. Because these points are isolated from this. So this is why I told now in the linear space, although we can do things of this nature, we can't, when the problem becomes more and more complex, it is not coming good. So that is where we go for non-linear techniques. One standard non-linear techniques available are things like kernel principal component analysis, where you try to map the linear space into non-linear spaces using kernels. And also there is a very good subject area which is being taught in mathematics courses, manifold learning. But the most important part that I am going to talk in the rest of the time is latent space. In latent space, we basically, I don't know whether there are still mathematical techniques for doing it, but here also it is sort of mathematics. But this is why which make it more interesting to learn or invent new mathematical techniques of doing, because here still we can't explain why certain things are happening like that. For example, I don't know how my faces are mapped into emotion space like this. But if you can do it mathematically, we can explain it. Right? But in neural networks, there are new areas like explainable AI. So in this kind of thing, we can explain why it happens. But I think mathematically also there should be some development. But this whole neural network can be explained as a mathematical function, where you have your original images here. They are mapped into a lower dimensional space. Lower means relative to this a lower dimensional space by introducing a bottleneck here. And again map back to the same dimensional space, where you try to make the error between x and exact minimum. So that means you are giving the input images and train the network so that you get the output also same. Right? Then by looking at this in between bottleneck neurons is the what we call as the latent space. So it is similar to the nonlinear version of principal component analysis in a way, where it is a nonlinear function which map it to a lower dimensional space and then we map it to the high dimensional space again. Right? So in this nonlinear space, various emotions, head poses, various things can be found to be represented using different feature vectors. And then by doing the animation, so for example this color changing, if you want to do it more naturally, although I have shown you how to do it using principal components, you don't get a very nice color change, more natural color change. But in the nonlinear space, you do the same thing where you map it into a certain color space and then make the necessary change so that color becomes warm. Right? And then reconstruct the image. So this is an example of a latent space. You send it through this set of, we call this as the encoder. And this is the latent space. You decode it, you get the original image back. But here you can find different vectors which are representing different features. So that is the book I mentioned. Right? In Berkeley University, you can freely download this book. It is available. Actually, this is not a new subject area. I have shown this to Professor Susant, and he told it is a collection of different areas in mathematics into one area. But this subject area is now developing. That's why they have named it as Invitation to Nonlinear Algebra. Very interesting book. And also, when you do different animations, we are using, rather than in the previous example, I have shown you the linear interpolation between two feature vectors, so that the emotion change. There also you got it naturally. But for more advanced, more natural changes, we want to study these spaces and things like Riemann interpolation, which are widely discussed subjects these days. I remember there was one of our students who did his PhD completely on, his PhD was on Riemann surface. Okay. So with that, you get the chance to now move to different spaces. Now, one example is, now this lady is holding the mask here. But same image I can ask it to convert. A small boy is holding a Kerala mask. So what it will do is map this onto a feature space like this, and then transfer the woman to boy vector area. Later I will tell you how this is exactly done, and then mask from this to this, or an old man holding a box. Things like this is possible in the vector space. So I will quickly go through this. And this is the most interesting part, the nature. Nature is always, I see, it is patterns plus randomness. Both are mathematical. Patterns also mathematically explainable, randomness also mathematically explainable. By combining them, you can go to very high level. In this case, in the latent space, the next step is modeling these clusters using statistical models. So you model, okay, Sri Lankan woman. Rather than having one vector, it is a cluster of points, and you can statistically model them. This we call as variational autoencoders, VAE, if you want to search for this. Now using this, we can synthesize images. Right? If you say you want to generate the Sri Lankan image, you can get a sample from that random probability distribution, and then send it through the decoder part, and decoder will generate the image. Right? Then there is another phase to check whether this image is good. But this is the basic idea. So various things like facial expressions, skin color, various things can be modeled using simple Gaussian models or more complex models. So more research is needed for these kind of things to make it more natural. Because the clients, what they need is more natural recreations. Okay, so now let's come to the other two examples. So all these are about the latent space, how we create different things.
දැන් නම් මට එපා වෙලා. ඔයාලටත් එහෙමද?
Well, anyway, so let us go to the other two areas. One is the modeling the body features, so animation, and then the movements. Last year. So in the early days, the facial movements were modeled using key points of the face. You can use principal component analysis to find the key points of the face also. But anyway, there are defined key points of the face to define animation. The relative position of them define different emotion. That is what the technology used earlier. Then you have linear algebraic transformation which will create different emotions. But now, these things are done on a latent space like this, where different emotions or causes, they are mapped onto spaces like this. And then, the other thing is body structure. Right? So this is a female body, and you have various points which are critical points of the body, which comes from the anatomy side. And then all these point vectors, I mean these are 3D coordinate vectors. Right? So you can easily represent them on the feature space. And then the most important thing is mapping them onto a latent space, which even without going to latent space also these things can be modeled. Things like height. So what are the parameters corresponding to height? Different areas corresponding to the body mass index and the age. So this is something that I have downloaded from somewhere. But you can create various body models. Right? So when you say I want a fat woman, fat old woman, you can easily transform from this feature space to that model. Similarly, movements. So again, here it is not only a particular critical position, but there are relative movements that is modeled mathematically, and later they can be mapped onto parameter spaces like femaleness or relaxing nature, things like that. Then the main idea is to, by controlling these parameters, you change how they move. So this is a very interesting area where we are trying to model dancing poses. I think there is a lot of research being done in modeling the dancing poses. It is already mapped into latent space. That is how we got that Giridevi dance also. And now it is being applied to robotics also. Please watch this full video, because this is a video which has taken the whole world by surprise this year in the China One exhibition. Especially countries like America, it is reported that they are getting really afraid by watching this performance, because these robots have adapted very natural human movements. Right? So how is it modeled? Robotics is one area, but how these natural human movements are incorporated into it. So soon we will find a robot to replace someone like Senara. So that's the future. So if you want to survive in this era, there's a huge discussion going on. Recently I had the time to, I got some invitation to comment on dance performance by the fine art department. Yeah, final evaluation. So one question they asked me also the same. So with all these things, will AI be a threat to human creativity? But all who have seen this, some people feel like it. So what is your opinion? For sure, we can replace the Canadian dancer very soon, because if you can have that kind of movement, I think it is just a matter of programming. To answer this, again, I have extracted one comment by one of you recently, and she has seen one of my creations. This is, I thank her for this idea. art is no longer about technical perfection. Art is the expression of human imperfection and the raw beauty found within. That is exactly the comment I gave to these art faculty people. All these dances that you are doing by learning can be replaced. But these features, the human expression, you cannot, I think, match. So the answer to that question I asked you, no, as long as humans stay human. So while doing all these things, please keep this also in your mind. And also this makes us to go and do more and more innovative art also, not only innovations in mathematics and AI, but in art also. So thank you.
Thank you very much, sir, for that insightful and engaging presentation. Now it's time for the Q&A session. So due to the tight time constraint, we only have time for a quick Q&A session. So it would be really appreciated if you can quickly ask any questions you have, raise your hand, and please feel free to share your thoughts.
Sir, in the BCA analysis,
Pardon?
we have an image, we do a BCA, so we identify different clusters. So if one of the clusters can represent the, non-visible feature of the image.
Yes, that is what sometimes happens in this multispectral and hyperspectral imaging also. The things which you cannot directly see on a normal space can be extracted in a, especially now here I am showing you the simulation using the principal component, most dominant one. But if you go for the other components which I haven't calculated, or of the computational constraint, some of the components cannot be calculated. Right? But if you analyze those features, they are representing various other things. I will give you one example in one of the projects that we have done. We wanted to extract the, I think I have shown this to many groups here, baby's heart rate from a mother's heart signal, which is hidden there. But when you analyze the less dominant principal component, we found it is corresponding to the baby's heart or fetal heart. So like that, even in an image, directly non-visible features like cracks on a concrete surface or some cracks on gear wheel which are covered with rust. When you go to that space, sometimes you can analyze. Only thing is finding out which vectors or which components are covering that area.
Yeah, how we identify the feature? If we don't know feature, we don't know that happens because of a crack on a concrete or something. We don't know that. But only a PCA test in a multispectral image shows the cluster. But how we can identify what it is the course of that?
Actually, that part I am also still learning. At the moment, the technique we use is we write a program and analyze each component and see. That's what we did for that stethoscope. Started from the first principal component and then remove that one and take the next one and see which is generating it. Then we get, okay, this area is the one which is corresponding to this information. Right? But I think there should be mathematical technique which I don't know. But I think it's a very interesting area. The same problem came once for water leak detection. Same thing. What are the components corresponding to a water leak? Yes, now for example, if you take that animation I have shown, facial animation, as you said, the first principal component defines the main face structure. And it was the second one which was represented. Actually what has happened there was, just because we are using similar set of faces, the second one was representing but when it came to the other thing, multiple faces came. This one. Here, since we are using a similar set of faces, you can see the poses were same. So that is why it works. But if you have a different poses and different sort of faces here as the original image, what you said will be coming. So then we have to go for more lower spaces. Because the main component will be defined in different basic structure. That's why this didn't work well. This worked well and this one didn't work well. Here, it is not getting clear image.
So in that case, we have visual
Yeah. Because here I have tried to first three. If I have used somewhat lower, but the advantage of non-linear spaces, with more lower dimension, you can get here it is a linear transformation.
Thank you. As we come to the end of today's seminar, I would like to express our sincere gratitude to Dr. Janaka Wijayakulasooriya for taking the time to share his expertise and for delivering such an insightful and inspiring session. We truly appreciate the valuable knowledge and perspectives you have shared with us. As a token of appreciation, I would now like to invite the President of the Engineering Mathematics Society, Mr. Rumal Dhammasiri, to come forward and present a token of appreciation for students. I would also like to extend my sincere thanks to all our participants for your enthusiasm and active participation throughout the session. Finally, our heartfelt appreciation goes to the Engineering Mathematics Society, the organizing committee, and everyone who worked behind the success of this event. Thank you all once again for being here. We hope you all enjoyed, and we look forward to seeing you all in the next MathXplore session. Thank you.